In today's lesson, we are going to be looking at the ambiguous case with the sine law. So this is going to be kind of an application of the cast rule, which we have previously looked at, and combining it with the sine law, which we've previously looked at as well, and which was reviewed from last year. So when using the sine law, it is sometimes not clear whether the unknown angle is acute or obtuse. And the reason that we have two possible angles is because of the cast rule. We know that there can be a ratio for sine that gives us two possible angles, one in the first quadrant and one in the second quadrant, or an acute and an obtuse angle. So this situation occurs when you are given an angle, the adjacent side, and the opposite side, and specifically when the opposite side is smaller than the adjacent side. If this is the case, then there are two possible triangles that can be drawn. And this is known as the ambiguous case because, again, we don't know which one it is based off of the information we're given. So first, given triangle ABC, angle B is 30 degrees, C is 12 centimeters, and B is 9 centimeters. So looking at this, I have an angle that's given, I have the opposite side, and I have an adjacent side. Now again, we don't really call them opposite and adjacent too often because we don't want them getting confused with the sine ratio for right angles, but at least in terms of description of where they're located in our triangle. So by looking at this, angle C here can be acute because this opposite side is shorter than the adjacent side. And the other way, where it's obtuse, I'll draw B, I'll draw A. Essentially, this opposite side can also come in to still form a triangle. It will still be 9 centimeters, this will still be 12, this will still be 30 degrees. But now this angle here is obtuse. And when we're going through and doing the calculations, we don't know which one it is. We don't know which angle it's going to be. Our calculator is only going to give us this version. Right? So our calculator is only going to give us the acute angle. We have to be aware, because of the cast rule, that there is a second angle that could also give us the same ratio. So I'm going to go through and do the sine law quickly to find out what the angle would be, because I have now a full pair and a half pair. So sine B over little b equals sine C over little c. I'm going to try to speed this up a little bit because we have looked at the sine law before, so that should be review. If not, again, please make sure you go back and take a look at that lesson. So we'd end up with sine C is equal to 12 sine 30 divided by 9. C equals the inverse sine of 0.67, that's rounded. And C equals, we get 42 degrees. So that's what you would get on your calculator, right? Similar to what we've done before, you would go through, that would be what you get on your calculator, which wouldn't be wrong. However, we want to be aware of the fact that there could be another scenario. Right, so right now we know that this angle exists, 42 degrees, with a positive ratio. The cast rule says, I'll write it in there, C-A-S-T. The cast rule tells us that we have another angle over here that would give us the same ratio. So in this case, we need to figure out what that angle would be. We're using the knowledge of the acute or the related acute angle, 42 degrees, to work backwards, and we would get, so C would also equal 180 minus 42. So C could also equal 138 degrees. So that is our other possible situation. Again, we're not going to know which one it is, unless depending on the situation or the context, it's a little bit more clear. But right now, we won't know which one it is. Our calculator will tell us one. It always tells us the acute. we want to be aware or check to see of just what the other possibility could be. So again, and sometimes the context of the question makes it clear which unknown or whether the unknown is acute or obtuse, maybe depending on the situation. Maybe it's clear, maybe there's more information in the triangle that tells us that. In other cases, we might be required just to calculate the two different solutions and just be aware of both. So let's go through and take a look at some of the possible scenarios. We're going to be given information for triangles. We want to determine if the ambiguous case exists, and if it does, then we want to calculate both angles. If it doesn't exist, we're not going to go through and calculate the angle because, again, we'll have plenty of practice with the sine law, and we've looked at it already. So triangle A, B, and C. So I'm going to draw a triangle. I'm going to roughly keep it similar to the version that we had on the previous page, at least the acute form, and try to label the information as much as possible so that I have this angle, this side, and this side. Just to keep it consistent, and then it's helpful when I'm going back and looking at other examples. I always know what I'm kind of looking for. So I know angle A, so let's put that down here. This is B50. I know side A across is 9, and I'm given side B. Let's call it that side, so let's call this B and this C. And we're asked, does the ambiguous case exist? Well, the opposite side is 9. The adjacent side is 8. The opposite is larger, so the ambiguous case does not exist. And the reason being, if you were to try to move this opposite side in, so obviously our sides aren't to scale, which is fine, right? Because we're just looking at the numbers. But if I was to move that longer side in and form an obtuse angle, it would look something like that. It's too long to pair up with the base side there. So it does not exist. So we're not going to go through and find angle B. The next one, triangle XYZ. XYZ, I know angle Z, so let's put that down here in the corner, 43 degrees. I know X and I know Y, right? So again, I don't know one of the two other sides. So in this case, it doesn't really matter which one we put it at. Let's put the largest side over here. So let's make this Y. So this is 18.7. We'll put the smaller side down here, 12.1. Just because that makes it a little bit easier, right? Because if it was larger than 12.1, maybe it was smaller than 18 point, or maybe it was smaller than 18.7 or larger than 18.7 as well. So again, it's just easier if we put the longest side here and see what we get. Now, I have an angle. I have the adjacent side. I don't have the opposite side. And even if I switch these two around, I still wouldn't have the opposite side. So let's go through and calculate. I do have a sandwiched angle, so that should tell us that we're using cosine law to find z squared. So z squared equals 12.1 squared plus 18.7 squared minus 2 times 12.1 times 18.7 cosine 43. Z squared will equal 165. And again, I'm going through this quickly because we have covered it already. Z equals square root 165. Z equals 12.8. So now that I can put 12.8 here, now I can make the comparison. Now I can check, is my opposite shorter than my adjacent? In this case, it is. 12.8 is shorter than 18.7. So therefore, it does exist. And now we have to go through and find what this angle is. Right? Because now we're going to go through and find the two scenarios for this angle, because we do know that the ambiguous case exists. I do have a full pair and a half pair now. So sine z over little z is equal to sine y over little y. sine 43 over 12.8 is equal to sine 18, oh, not sine y. We don't know what that angle is, or 18.7. We get sine y equals 18.7 sine 43 divided by 12.8. Y equals the inverse of sine of 0.996. We get y is equal to 85 degrees. So again, that is our acute angle. That is one possibility. Again, from the cast rule, again, you don't need to always draw the cast rule. This is just to, again, visualize it. If this is 85, I know I have to have an other angle in this side that also matches or has the same ratio. So that means that this angle is 85. So therefore, the other option for y would be 180 minus 85. We get y is equal to 95. Again, not drawn to scale. It's just more there to visualize the cast rule. So I know for this triangle, I could have y either being 85 or 95 degrees. Triangle, or example C, triangle STU, we have angle U, angle S, and side U. Okay, I'm going to go through and draw. Angle U, let's put down here, 37 degrees. I know side U is 13.5, and I know angle S, I'm going to put that here, is 72 degrees. So this would be side T. So we need to go through and check. Well, right now I don't have enough information to, I have an angle, I have the opposite side, I don't have either adjacent side, so I can't even like rotate this triangle around and find it. But I do have two angles, and we should know that if we have two angles, the third angle is going to be 180 minus 37 minus 72, which in this case we get to be 71 degrees. So that means this is 71 degrees. Because I already know two angles, there is no possible scenario where this other angle could change. Based on the fact that I know what my two angles are, there's only one other option for that third angle. So therefore, in this case, it does not exist. And again, in these other two examples, we don't know this top angle here. We don't know what those are. So in reality, maybe if we were given those angles, the ambiguous case wouldn't exist. Right? We don't know. Right? So again, if we were given other information, then maybe we know for sure what type of angle it is, but we don't. So in this case, with the information provided, there's no way that we could have an ambiguous case, because based off the fact that we already have two angles, that third angle there's only one possible option. D, JKL, again, I know side J, or angle J, so 60 degrees. Side J is 7, K is 8. So again, I can place K wherever I want. Because I'm given one other side, I'm going to put K here. I'm going to put K to make it the adjacent, so I do have enough information to check and see if this angle is ambiguous or not. And in this case, it is. My opposite, 7, is shorter than the adjacent, 8. So this could move in and make an obtuse angle for K. So therefore, it does exist. And now we need to go through and figure out what that angle is. So we're going to use our sine law. So sine J over little j is equal to sine K over little k, and very similar to what we've done before. So sine 60 over 7 is equal to sine K over 8. Sine K equals 8 sine 60 divided by 7. K equals the inverse of sine of 0.989. And we get K is equal to 81 degrees. So K is 81 degrees. Again, using the cast rule now for the other one. We know right now, based off the ratio, 81 degrees. But the cast rule says that there's going to be another angle on the other side. So using that acute angle that we were given, we can use that to find what the possible second angle is. So K could also equal 180 minus 81. K could equal 99 degrees. So again, those are the two possibilities now. K could be 81, it could be 99. We don't know. If we're given more information, it might make it clear, but right now we don't know, and that's just the point. We just want to make sure we're aware that there are two possible cases for this triangle. All right, so let's take this concept and try to apply it to a real world situation in terms of maybe design or engineering. So a light near a path can safely illuminate up to a distance of 50 meters. A point on the path is 75 meters from the light. So we have our point here. It's 75 meters from our light. The sight line to the light makes an angle of 26 degrees with the path. What length of the path is safely illuminated? Well, I know this light is going to be able to reach out to this point here. It should be able to. In 50 meters. That's given from the information, right? Distance of 50 meters, angle of 26. The point on the path is 25 meters from the light. So I know this triangle right now. So I could figure out the total length of the path. But I want to know what length of the path is illuminated. So if we think about it, and I'm just going to do a quick drawing here. Or if we think overhead, if this is my light, when it emits the light, it's only reaching out 50 meters. Right? So it's not going to touch everything along that path. The distance from the one end is 75 meters. It's only going to reach, say, 50 meters in the one direction, and then there's going to be 25 meters that isn't illuminated. Right? So it's not going to cover everything. So if we think about this light extends 50 meters here, and it's going to maybe extend 50 meters in another direction. We want to know if that's possible. Well, if we look at our triangle, we have an angle, we have the adjacent side, and we have the opposite side. So we have enough information to check to see, is there an ambiguous case? Is this allowed to work where we have an obtuse angle here and an acute angle here, depending on the triangle? Well, the opposite is shorter. So yes, this light could drift in, make a new triangle that has an obtuse angle. So we can use the ambiguous case to help us solve this problem. Right, so I'm just going to put down that it is the ambiguous case, just so we're aware that we are going to have to find one angle and go through and find it again. What we're going to do first is find out what is that angle to begin with. What is this angle here? We know there's going to be an ambiguous case, but I need to find that angle first. So I'm going to do the sine law. So we'll do sine of 26 over 50 is equal to sine of, we'll call it P for path, over 75. Sine P is equal to 75 sine 26 divided by 50. P equals the inverse of sine, 0.657. P equals 41 degrees. So I know that angle P can be 41 degrees. So that means I can have one triangle (50, 75, 26, and 41 degrees. I can figure out this third angle, which I'm going to need. 180 minus 26 minus 41 equals 113. And the reason we're finding this angle is because we want to know what is this side, what is this length, what is the length of the path. So we're going to use sine law again. Sine of 113 over x is equal to sine 26 over 50. X is equal to 50 sine 113 divided by sine 26. And x will be equal to 105. Say meters. So that means that the entire pathway from the person to the farthest point where the light reaches is 105 meters. However, the light does not always reach the entire pathway. So we need to figure out the ambiguous case. We need to figure out, okay, what's the closest, or what's the closest to the person that this 50 meters of light reaches. So I know that this is 26 still. This is 75. This is 50. This is going to be a new angle. That new angle, let me actually just draw this triangle a little bit bigger so the numbers aren't as crunched. So 26 degrees, 75 meters, 50 meters. I don't know that length. This angle is going to come from the ambiguous case, or the cast rule. So if I know I have an angle here that's 41 degrees, then the obtuse angle is going to pair up with that. So I'm going to use the acute of 41 degrees, and we'll say P can equal 180 minus 41, which is the same as 139. So that means that this angle here is 139 degrees in the ambiguous case. That then changes what this small angle is. This small angle is now 180 minus 26 minus 139, which equals 15 degrees. So now I'm going to go through and do the exact same calculation, except solve for that unknown. I'm going to skip it, or I'll at least write out the main one. So sine of 15 now over y is equal to sine 26 over 50. That doesn't change. Y equals 50 sine 15 divided by sine 26. So all we did was the exact same question, or the exact same calculation. We've just changed from 113 to 15 based on what this angle is, or the ambiguous case. And then we get y is equal to, if we do 50 sine 15 divided by sine 26, we get roughly 30 meters. So why did I need to find two distances? Well, let's draw a diagram, like an overhead view of, again, we got our lamppost. There's our lamppost. Here's our walkway, our pathway. Here's our person. Again, remember they're 75 meters from that lamppost. So they're not going to even be covered in light from that lamppost. But we do know two things. We do know, one, the lamppost can reach over here, which tells us that the entire pathway from here to here is 105 meters. We also know that the light will cover a certain amount of path, and the closest it will get, again going 50 meters, is here. That would make this distance from the person to this point 30 meters. So all that's saying is the light is going to go from here to here. That's kind of, right, if we think of like an arc of the light, or a triangle coming out, it's going to cover that much. We need to figure out, or the question is asking us, what is that distance? So the illuminated part, we'll just call it I, is equal to 105 minus 30, which equals 75 meters. So therefore, the light covers 75 meters of pathway. So it'll cover 75 meters of that pathway. So again, this was more of just an application of the ambiguous case, right? Just looking at, is there an ambiguous case, and using the two different triangles to find us a certain section. In this case, a certain section that is illuminated. It's all using the sine law, which you'll primarily be using unless you need to use the cosine law to find a missing piece, similar to what we did back here in example B. But again, the main thing that I want you to be able to do is, one, understand what the ambiguous case is, and two, be able to check to see if there's an ambiguous case. And then finally, three, figure out what the two possible angles could be. The calculation should be relatively straightforward. It's the same things that we've been looking at through so far. Now it's just looking for a specific scenario.